conversion. If the data is digital one, so we can convert the digital data into digital signal using line coding schemes. But if the signal or information, if it is analog one, that means analog information is to be exchanged between the sending node and the receiving node. So in such instance, analog data need to be converted into digital signal. So that is called as analog to digital conversion. So in the case of analog to digital conversion, the input information will be in terms of analog form, and through the transmission media, the analog information will be converted into digital signal. Once again, at the receiver side, the digital signals can be converted back into the analog signal, analog data, in order to get back our original information. Converts digital data or analog signal to digital signals. Analog signal may be in the form of microphone or camera. Two techniques we can consider which converts analog informations into digital one. So the first technique is pulse code modulation. In short, we can call it as PCM. And the second one is called as delta modulation. So first we can consider pulse code modulation or PCM, which is the most common technique which can change an analog signal into digital data. That means digitization. Components of PCM encoder. So PCM encoder has three different processes like sampling, quantization and encoding. So here we can clearly observe that the input given to the PCM encoder block is analog signal and the output of the PCM encoder block is digital data. So that means the analog signal is converted into digital data, which is called as analog to digital conversion. So PCM encoder has three processes. The first one is the analog signal is sampled. After sampling, the sampled signal is quantized. After quantization, the quantized value are encoded as stream of bits. That means the quantized values can be encoded into patterns of zeros and ones. So first we can consider the first process, which is called as sampling. The analog signal is sampled at every TS seconds, where TS is called as sampling interval or sample interval or period. The inverse of sampling interval, we can call it as sampling frequency, and we can compute the sampling frequency Fs is the reciprocal of sampling rate. Sampling frequency is equal to 1 by Ts. So under sampling, we are having three different methods. The first one is ideal sampling. Second one is natural sampling, and the third one is flat top sampling. So first we can consider ideal sampling. In the case of ideal sampling, pulses from analog signals can be sampled. Pulses of analog signals can be sampled. But this kind of ideal sampling cannot easily implemented. So next we can take the second sampling method, which is called as natural sampling. So in the case of natural sampling, a high speed switch is turned on. So here we are using one high speed switch. High speed switch can be used, and whenever this switch is turned on for only the small period of time when the sampling occurs. So this high speed switch will be turned on for a shorter duration where exactly the sampling occurs. So because of this, we can have sequence of samples that retains the shape of the analog signal. So since we used one high-speed switch and that particular switch will be turned on for shorter duration, so because of that the sampling will take place and will have a sequence of samples that retains the shape of the analog signal. So the last one is flat top sampling. In the case of flat top sampling, so we can make use of sample and hold circuit. We can make use of sample and hold circuit. So by which we can have the different samples, or we can have the sequence of samples can be obtained after sampling process. So these are the three different sampling processes. The first one is ideal sampling, in which the pulses from the analog signals can be sampled. The second one is natural sampling, where we can use high-speed switch in order to sample the signal or analog signal. So the last one is flat top sampling, where we can make use of sample and hold circuit in order to perform the sampling process. So in the case of ideal sampling, pulses from the analog signals are sampled. This is an ideal sampling method and cannot be easily implemented. In natural sampling, as I mentioned before, we can make use of high-speed switch. And the last one is the most common sampling method called as sample and hold circuit. However, this creates the flat top samples by using a circuit. Important consideration is sampling rate or frequency. So now, what may be the restriction on sampling rate? So, suppose if you are considering the Nyquist equation, according to Nyquist theorem, the sampling rate it should be at least 2 times the maximum frequency contained in the signal. In order to reproduce the original analog signal, one necessary condition is that the sampling rate be at least twice the highest frequency in the original signal. Nyquist sampling rate for low pass and high pass signals. So if the analog signal is low pass, then the bandwidth and the highest frequency it will be same. So bandwidth is equal to maximum frequency itself. So if the signal is low pass signal, the value of the bandwidth and maximum frequency both are same. If the analog signal is band pass signal, then the bandwidth value will be lower than the maximum frequency. If the analog signal is band pass signal, the value of bandwidth it will be lesser than the maximum frequency. So in other words, we can say that as per the Nyquist theorem, the sampling rate must be at least 2 times the highest frequency contained in the signal, as well as we need to have the finite bandwidth. Then only we can sample the signal. Quantization. The following are the steps in quantization. First, we have to assume the original analog signal has instantaneous amplitude between maximum to minimum. So we can have the maximum voltage as Vmax and minimum voltage level we can consider it as Vminimum. So we can divide the range into L different zones, each of height delta. So we can compute the value of delta as Vmax minus Vminimum divided by total number of levels L. So that means L zones. So we assign the quantization values from 0 to L minus 1 to the midpoint of each zone. So that is, quantization values can be assigned to the midpoint of each zone. So later we have to go for approximation process. So that is, we approximate the value of the sample amplitude to the quantized values. So as a simple example, we assume that we have a sample signal and the sample amplitudes are between -20 to +20, and we are having the value of L as 8. So this means that we can compute the value of delta as Vmax minus Vminimum divided by L. So Vmax is +20 minus -20 divided by 8. So that is equal to 40 by 8, that is equal to 5. So therefore the value of delta, we can get it as 5. So quantization and encoding of a sample signal. Quantization levels. The choice of L, that is the number of levels, depends upon range of the amplitude of the analog signal. If the amplitude of analog signal which fluctuates between two different values only, then we can have only two levels. That means L is equal to 2. If the signal like voice has many amplitude values, we have to consider more number of quantization levels. So in the case of audio digitizing, L is normally chosen as 256. In the case of video, it is normally in terms of few thousands. Choosing lower values of L increases the quantization error. So in order to achieve better or errorless quantization, we need to have the value of L as higher value. If there is a lot of fluctuations in the signal, so that means if the value of L is low, then obviously there may be chance of quantization error if there is a lot of fluctuations in the signal. Quantization error. Quantization is an approximation process. If the input values to be quantized are real values, the output values are the approximated values. The output values are chosen to be the middle value in the zone. If the input value is also at the middle of the zone, there is no quantization error. Otherwise, there is an error. So, if we are calculating the output values, can be chosen from the middle value in the zone. If the input value is also at the middle of the zone, what happens is, so if you are considering the input values is also at the middle of the zone, there is no quantization error. Else, obviously, there may be a chance of quantization error. The quantization error changes the signal to noise ratio of the signal. That means it changes SNR value, which in turn reduces the upper limit capacity according to Shannon theorem. So in this example, we can consider the quantization codes like it varies from 0 to 7, and the normalized values are given in the x-axis along with the time zone. So now here we can observe that we are having normalized values, pulse amplitude modulation values as -1.2, 1.50, 3.24, 3.94, 2.20, -1.10 and so on. Similarly, the normalized values are this one, -1.50. So this is the approximation process. 3.50, 3.50 and so on. So now we have to compute the normalized error. That means normalized PAM value minus normalized quantized value. So that means, suppose for this example, we'll take one value. So normalized PAM value, pulse amplitude modulation value is minus 1.22 minus of 1.50. So you can get the normalized error as minus 0.38. Similarly for second one, 1.50 minus 1.50. So here we'll get the normalized error as 0. 3.40 we get 0.25 and so on. So now we have to write the quantization codes according to the normalized PAM value. So here we are having the normalized PAM value is minus 1.22. So that is almost over here. Minus 1.22. The quantized value is 2. So similarly, 1 plus 1.50. This is 1. D means 1. 1.50. Quantized value is 5. And so next is 3.24. The quantized value approximated will be equal to 7 and so on. So finally we can convert the quantization code into encoded words by representing in terms of binary value. So 2 means 0, 1, 0, 5 means 1, 0, 1, 7 means 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 1 and 0, 1, 0, 0, 1, 0 and so on. So what is the value of SNR in terms of dB? If we have 8 levels and 3 bits per sample. So we can compute SNR dB as SNR in terms of dB, that is equal to 6.02 NB plus 1.76 dB, where NB is equal to, we have NB is equal to number of bits per sample, in this case NB is equal to 3. So we can compute SNR dB as 6.02 into 3 plus 1.76 dB. So we'll get the answer as 19.82 dB. Encoding. The last step in PCM is encoding. After each sample is quantized, the number of bits per sample is decided. Each sample can be changed to an NB bit code word. So suppose the quantization code is 2. Suppose the quantization code is 2. We can encode as 0, 1, 0. If it is the quantization code value is 5, we can encode it as 1, 0, 1 and so on. We want to digitize the human voice. What is the bit rate assuming 8 bits per sample? The human voice normally contains frequencies from 0 to 4000 Hz. So therefore, we can compute the sampling rate. It will be always twice the maximum frequency. So that means 2 into 4000 hertz, so that is equal to 8000 samples per second. So now we have to compute the bit rate. Bit rate equal to sampling rate into number of bits per sample. So in this case, sampling rate is 8K, that is 8000 samples per second into, we need 8 bits per sample. So we can get the solution as 64 kilobits per second. A telephone subscriber line must have an SNR dB above 40. What is the minimum number of bits per sample? So we are having the equation SNR dB is equal to 6.02 MB plus 1.76. So here SNR dB is given as 40 is equal to 6.02 MB plus 1.76. So now on simplification we'll get number of bits per sample NB as 6.35. Original signal recovery. So the recovery of the original signal requires PCM decoder block. PCM decoder block. Why? Because the PCM encoder which converts analog signal to digital data or digital pattern. So now once again we have to get back our original signal. So that is from digital to analog. The decoder first uses circuitry to convert the code words into a pulse that holds the amplitude until the next pulse. After the state gauge signal is completed, it is passed through the low pass filter in order to smooth the state gauge signal into an analog signal. So we can also make use of filters that has the same cutoff frequency as the original signal at the center. So the diagram shows the major components of PCM decoder block. So in the PCM decoder, we can clearly observe that we are having the digital data, and the PCM decoder has make and connect sample block as well as low pass filter. So the output of the low pass filter, it will be the actual analog signal which is transmitted from the sender side. PCM bandwidth. The minimum bandwidth of a line encoded signal is B minimum is equal to C into N into 1 by R. So now B minimum is equal to C into N into 1 by R, where N is equal to NB into Fs into 1 by R, but Fs is equal to 2 times P analog into 1 by R. When 1 by R is equal to 1 for NRZ and polar scheme, if the value of C is equal to half, that is, in the case of average situation, the minimum bandwidth can be computed as B minimum is equal to NB into B analog. Minimum data rate of a channel. The Nyquist theorem, which gives the data rate of a channel as Nmax equal to 2 into bandwidth into log 2 to the base 2 of L bits per second. So we can reduce this rate from the Nyquist sampling theorem. That means the minimum required bandwidth B minimum is equal to N divided by 2 into log 2 to the base 2 of L in terms of hertz. So this is the equation in order to calculate the minimum bandwidth required. We have a low pass analog signal of 4 kilohertz. If we send the analog signal, we need a channel with a minimum bandwidth which will be around 4 kilohertz itself. But if we digitize the signal and send 8 bits per sample, so now the minimum bandwidth B minimum is equal to NB into B analog. So that is equal to 8 bits into 4 kilohertz. So that is equal to 32 kilohertz. So if we digitize the signal and if we want to send 8 bits per sample, then the minimum bandwidth will be equal to 32 kilohertz.